Two cars leave the same location at the same time. One is traveling due east at 60 kilometers per hour, the other one due north at 45 kilometers per hour. How fast are they separating? How fast are they going apart when they have been traveling already for 2 hours? So what we're going to do first in this one is we're going to say, well, this 60 kilometers per hour is a rate of change. I'm going to call this is my x-axis, this is my y-axis. I'm going to label these x, y, and z. And so what we already know is we know dx dt is equal to 60 kilometers per hour. We know dy dt is 45 kilometers per hour. And we want to find dz dt. And so that tells us that each of these are a function of time. This one's different than the questions we've had before because there's three things, well, there's two things that we know and a third thing we want to find out. So we have to kind of ask ourselves, do we know a relationship between x, y, and z that we could write a formula for? A squared plus b squared equals c squared, and in this case it would be x squared plus y squared equals z squared. What do we know at 2 hours? We know the distances, right? So we could draw a triangle for that. In 2 hours, you would go 120 in this direction. You would go 90 in this direction. And if you did a squared plus b squared equals c squared, anybody recognize those numbers? Can able to do that mental math in your head? 150. Nice. It's a 3, 4, 5 triangle, just multiplied by 30. So 3 times 30 is 90, 4 times 30 is 120, so 5 times 30 would be 150. So this is how far you've gone in 2 hours, and at that moment they're 150 kilometers apart. So what can we do? Well, we can take the derivative with respect of time of this whole thing. So when you get to your x squared, well, the derivative would be 2x, and then the chain rule would say dx dt. When you get to y, that would be 2y dy dt. And when you get to z, that would be 2z dz dt. Do we have all the information that we need to plug things in to find what we want? Yes. So what we can do is we've got our x is 120, dx dt was 60 kilometers per hour. Our y is 90, dy dt is 45 kilometers per hour. Our z is 150, and we want to find out what dz dt is. Okay. You can rearrange this with your calculator or however you like. Anybody see any mental math shortcuts that I did to figure this out? You could do some dividing things, right? You could divide everything by 2 and cancel out 2's and stuff like that. What I basically did as a visual for this is I said, well, 2 times 60 is 120. So basically this first one is 120 squared. And 2 times 45 is 90, so basically this second one is 90 squared. We already figured out what 90 squared plus 120 squared is from a squared plus b squared equals c squared. I knew this had to be 150 squared. And so this would have to be 75 for that to work. Okay? But you can still type this all into your calculator and figure that out that way as well. So our dz dt, that's 75. That means they are separating at 75 kilometers per hour. Now, because it's a right-angled triangle in this one, if we go back to our original triangle, and if you would have done a squared plus b squared equals c squared with the 45 kilometers per hour and the 60 kilometers per hour, you would have got 75 kilometers per hour as well. But it's nice to see how even an equation with 3 variables you can do implicit differentiation for. So some of our previous questions that had radius and height, if you knew what the dr dt was for that radius, then you could have done the derivative with 3 different variables in there and had dr dt's, dh dt's, and dv dt's in there. Just gets a little bit more complicated. So it's always nice. This case we did have 2 of the pieces of information. Then we could take the derivative on their own. Yes? This one right here, where we got these numbers? Well, it says to figure it out at 2 hours. And if you're going 60 kilometers an hour east, in 2 hours you'll have gone 120. So we could put some units here to say this is actually distances. That's how far you've traveled at that point. Okay, this example is exactly the same, so we're going to actually skip it. If you want to try it on your own after, that's fine. We'll go on to the latter question. So we have a 20-foot ladder leaning against a house. The ladder starts sliding away from the house, so the top of the ladder is also sliding down the house. So draw a picture of this. Here's our house. There's our ladder. It's 20 feet long. We're going to assume our house is at a right angle. It's not a crazy leaning Tower of Pisa or anything. And we want to find the rate at which the ladder is moving down. So if I make this y and this x, what do we know? We want to find out what dy dt is, which means y is a function of time. We know what dx dt is, because the bottom of the ladder is moving at a rate of 2 feet per second. Now, when I write dx dt, and this is going to be important, is at this point, can you see, is x going to be getting bigger or smaller? It's going to be getting bigger. So we're going to show that by writing this 2 feet per second as a positive number. What's going to be happening to y as that ladder goes down? That y is going to be decreasing. So what we're going to find is when we solve for dy dt, we're going to get a negative value as our answer to show that that's actually decreasing, that your y value is getting smaller. Yes? It's just, we're just imagining it as a straight ladder, single aluminum hard piece, straight line. Yes? Right. So how do we use, we're wanting to find out when x is equal to 12, at that moment, how fast is it decreasing? Okay? And so we could solve this question when x was 8 feet away, when x is 3 feet away, all sorts of different lengths. So what we're trying to figure out is if you were climbing this ladder and you were right at the top and you got right at the top and then the bottom of the ladder started to go out and it started to move away at 2 feet per second, how fast are you going down at this moment? Things aren't looking good, but how fast are you going down at that moment? Right? We could figure out how fast will you be going when you hit the ground if this continues that way, right? So, how do we set up a relationship between x and y in this case? Again, we can use a squared plus b squared equals c squared. X and y both change, but can you see this time your hypotenuse is always 20. So we got x squared plus y squared equals 20 squared. And if we take the derivative of this whole equation with respect to time, what do we get? 2x dx dt plus 2y dy dt, and the derivative of 400 will be 0. So notice here, when we go to look, what do we want to find? We want to find dy dt. Do we know x? Yes, when x is 12. Do we know dx dt? Yes. That was moving at 2 meters per second. But we don't know y, and we want to find dy dt. So in order to find dy dt, we do need to have a number in there for y. Now, if we look at our situation, we look at our ladder, when x is 12, what would be the other length? A squared plus b squared equals c squared, and you could solve for it. Do you recognize it? 16. It's another 3, 4, 5 triangle. Of course, if you don't recognize it, you can go and calculate it. So this will be 16. When we solve this, here we're going to get 24 times 2 is 48. Move that over to the other side. Divide by 32. And so we get negative 48 over 32. Simplifies to negative 3.2. Now, when I write my sentence, is it okay if I don't include the negative right there? I've said my direction when I say it's moving down. Okay? So the negative 1.5 that comes up in my answer is telling me which direction it's going, that your y value is decreasing. And then when you go about solving it, then you could write your statement just because you say it's moving down, that explains its direction as well. Okay? That's where we're going to stop for today, and you can work on some more of the ones from the homework. And then on Monday, we'll do the last similar triangle problem there, and we'll do some angle problems. So I'm going to give you an extra piece of paper, additional notes for some angle questions. And then on Wednesday, we'll have our quiz.